welcome to this problem walkthrough. Today, we'll explore problem number 954, array of doubled pairs. This problem challenges us to find if an array can be reordered into pairs where one element is double the other. Stick around as we dive into the details and approaches to solve this interesting problem. In this problem, we are given an integer array called ARR, and its length is guaranteed to be even. The goal is to determine whether it is possible to reorder the elements of the array such that, for every pair of elements at indices 2*i and 2*i plus 1, the second element in the pair is exactly double the first. If such a reordering is possible, the function should return true, otherwise, it should return false. The input is a single integer array, and the output is a Boolean value. Essentially, we need to verify if the array can be grouped into pairs where one value is twice the other. Let's explore this further with some examples to clarify how this works. Take the first example, where the input array is 3, 1, 3, 6. Here, the output is false. Why? Because no matter how we attempt to reorder the array, we cannot form pairs where one element is double the other. For instance, while 3 could pair with 6, this leaves us with 1 and another 3, which cannot form a valid pair. Now consider a second example, 2, 4, 0, 0, 8, 1, 16, 2. In this case, the output is true, as it is possible to reorder the array into valid pairs. For instance, we could pair 0 with 0, 1 with 2, 2 with 4, and 8 with 16. Each of these pairs satisfies the condition that one element is double the other, making this a valid reordering. In the third example, the input array is 4, minus 2, 2, minus 4, and the output here is true. A valid reordering would pair -2 with -4 and 2 with 4. This demonstrates that the solution must handle both positive and negative numbers appropriately. Moving on to the constraints, the array length can range from 2 to 30,000, and it will always be even. Additionally, the array elements can range from -100,000 to 100,000. Some important edge cases to consider include handling negative numbers, ensuring zeros are only paired with other zeros, and efficiently processing very large arrays. Duplicate values in the array can also make pairing trickier, and if any value cannot be paired, the function must return false. These constraints and edge cases highlight the importance of designing an efficient and robust solution for this problem. To tackle the problem of determining if an array can be reordered into pairs where one element is double the other, one approach we could consider is brute force. This involves generating all possible permutations of the array and checking if any of them satisfy the condition that, for every valid pair, the second element is exactly double the first. While conceptually simple, this approach is computationally prohibitive. The reason lies in the factorial time complexity required to generate all permutations and O(n) operation. On top of that, checking each permutation to verify the pairing condition adds further overhead. The result is a method that becomes impractical even for arrays of moderate size. While the brute force approach may be easy to understand, the trade-off is its extreme inefficiency, making it unsuitable for real-world use cases where performance matters. A much more efficient strategy uses a combination of sorting and hashing to solve the problem systematically. By sorting the array based on the absolute values of the elements, we ensure that smaller magnitude numbers are processed before larger ones. This is crucial to avoid invalid pairings, especially when dealing with negative numbers or zeros. The process starts by creating a frequency map, or counter, to track how many times each number appears in the array. Then, as we iterate through the sorted array, we attempt to pair each number x with its double, 2*x, by checking their counts in the frequency map. If a valid pair is found, we decrement the counts for both x and 2*x. If pairing is not possible at any step, we return false. Finally, if all numbers are successfully paired, we return true. This approach achieves a time complexity of O(n) log n, primarily due to the sorting step, and a space complexity of O(n) for the frequency map. The trade-offs here are clear. Although sorting adds a logarithmic factor to the complexity, it ensures correctness, and the use of additional space for hashing significantly speeds up the pairing process. The strategy we've chosen revolves around the insight that correct pairing depends on processing numbers in order of their magnitudes. By sorting the array based on absolute values, we guarantee that smaller numbers are handled first, which is particularly important when dealing with duplicates or zeros. Using a frequency map allows us to track how elements are used without modifying the original array, ensuring efficiency and precision. The moment of realization here is that sorting by absolute value eliminates the risk of incorrect pairings, while hashing enables quick lookup and management of element counts. This approach stands out because it balances both time and space efficiency while maintaining correctness. Brute force, as we discussed earlier, is too slow, and no other method can outperform the O and log n complexity achieved here. While sorting introduces some computational overhead, it is indispensable for ensuring valid pairings. Similarly, the extra space required for the hash map is a reasonable trade-off for the significant gains in performance. In the end, this optimized approach is robust, efficient, and perfectly suited to handle the problem within competitive constraints, making it the clear choice. In this problem, our goal is to determine if we can reorder the given array so that every pair of numbers satisfies the condition where one number is double the other. Specifically, for each valid index I, the condition ARR 2 I plus 1 equals 2 ARR 2 I must hold. To solve this, we need to ensure that the array can be divided into pairs of the form x, 2x, where every number in the array is used exactly once. The task becomes challenging because the array can contain positive numbers, negative numbers, and zeros, and each of these cases requires careful handling. For example, zeros can only pair with other zeros. A key first step in the process is to sort the array by its absolute values. Sorting in this way ensures that, when iterating through the array, smaller numbers are processed before their potential doubles, making it easier to find valid pairs. For instance, in the array, -4, -2, 1, 2, 4, 8, sorting by absolute values produces 1, -2, 2, -4, 4, 8, which simplifies the pairing process by ensuring potential doubles appear later in the sequence. Once the array is sorted by absolute values, the next step is to use a frequency map to keep track of the count of each number. This frequency map allows us to efficiently determine how many instances of a number are available for pairing. For example, given the sorted array 1, -2, 2, -4, 4, 8, the frequency map becomes 1, 1, -2, 1, 2, 1, -4, 1, 4, 1, 8, 1. With this map in place, we can begin the greedy pairing process. For each number x in the array, we check whether it can form a pair x, 2x. If both x and 2x have counts greater than 0 in the frequency map, we reduce their counts, effectively marking them as paired. However, if x still has a positive count but 2x is unavailable, it means pairing is not possible, and we can return false immediately. Special attention is required for zeros, where the count must be even, as zeros can only pair with each other. Finally, when all numbers are paired, the frequency map should reflect 0 counts for every element. If any number remains unpaired, indicated by a non-zero count, the pairing is incomplete, and the result is false. Several key insights drive the efficiency of this algorithm. First, sorting by absolute values is crucial because it ensures that smaller numbers are processed before their potential doubles, reducing the likelihood of encountering unpairable numbers later. The frequency map plays a central role by allowing us to efficiently track and update the count of each number during the pairing process. Handling zeros requires special care since they can only pair with themselves, making it necessary to verify that the count of zeros is even. Additionally, the greedy pairing approach, which processes smaller absolute values first, helps prevent scenarios where a number is used up prematurely, leaving its double unpairable. The two main data structures used here are the frequency map, which provides efficient lookups and updates, and the sorted array by absolute values, which ensures the correct processing order. For example, with the array 1, -2, 2, -4, 4, 8, these structures work together seamlessly to facilitate the pairing process. When analyzing edge cases, there are several scenarios to consider. For zeros, if the count of zeros in the array is odd, pairing becomes impossible since zeros can only pair with other zeros. For negative numbers, the algorithm must ensure that they are handled correctly, as valid pairs can still be formed if both x and 2x are negative. Another edge case involves unpairable numbers, such as in the array 3, 6, 12. Here, after pairing 3 with 6, the number 12 remains unpaired, and the result is false. Regarding complexity, the time complexity is dominated by the sorting step, which takes O n log n, and the pairing process, which is O n, leading to an overall complexity of O n log n. The space complexity is O, n, due to the storage of the frequency map. Together, these considerations ensure that the algorithm is efficient and robust across a wide range of inputs. This Python solution to LeetCode problem number 954 uses a greedy approach to determine whether the array can be reordered to form doubled pairs. The idea is to pair elements in the array such that each pair consists of x and 2x. 1. Importing counter. The solution starts by importing the counter class from the collections module. This is used to count the occurrences of each number in the array. 2. Counting frequencies. The counter object is created to store the frequency of each number in the array. This helps us track how many of each number are available to form pairs. 3. Sorting keys by absolute value. The keys of the counter are sorted based on their absolute values. This step is critical for handling negative numbers correctly. Sorting ensures that smaller absolute values are processed first, which prevents mismatches when pairing numbers. For iterating through sorted keys, the solution iterates through the sorted keys. For each x, it checks whether there are enough 2x values to pair with all x values. If not, the function immediately returns false. 5. Forming pairs. When there are sufficient 2x values, their count is reduced by the number of x values used to form pairs. This ensures that no number is used more times than it appears in the array. 6. Returning the result. If all numbers are successfully paired, the function returns true. Otherwise, it returns false when a mismatch is detected. This approach is efficient due to the use of sorting and counter. Sorting ensures proper handling of negative numbers, and the counter operations, like subtraction, are fast. The overall time complexity is dominated by sorting, making it O, n log n. This solution handles all edge cases, including arrays with zeros, negatives, and duplicates, ensuring correctness in all scenarios. This is the Java implementation of LeetCode problem number 954, array of doubled pairs. The logic mirrors the Python solution, using a hash map to count element frequencies and sorting the keys based on absolute values to handle negatives correctly. Java-specific differences include explicit type declarations, usage of collections like hashmap and arrays, and handling boxed integers when sorting. The implementation ensures that all elements can be paired appropriately, adhering to the constraints of the problem. To solve this problem, we start with the given input array 4, -2, 2, -4. The first step is to calculate the frequency of each number using the counter class from Python's collections module. This results in count equals counter, 4, 1, -2, 1, 2, 1, -4, 1, which tells us that each number appears exactly once in the array. Next, to handle both positive and negative numbers properly, we sort the keys of the count dictionary by their absolute values. This gives us the sorted order, sorted_keys equals, -2, 2, 4, -4. Now, we iterate through these sorted keys. Starting with the key -2, we observe that count -2 equals 1 and count -4 equals 1. Since count -2 is less than or equal to count 2 asterisk -2, we reduce count -4 by count -2. This operation updates the counts to count equals counter, 4, 1, -2, 1, 2, 1, -4, 0. This ensures that we are correctly pairing -2 and -4. Continuing with the next key, 2, we find that count 2 equals 1 and count 4 equals 1. Again, since count 2 is less than or equal to count 2 by 2, we reduce count 4 by count 2. This results in count equals counter, for a clock, -2, 1, 2, 1, -4, 0. Next, we process the key 4. Here, count 4 equals 0, so there's nothing further to do for this key. Similarly, for the key -4, count -4 equals 0, so no further action is needed. Finally, we perform a check to confirm that all counts are 0. Since every value in the count dictionary is 0, it means that all numbers have been successfully paired. Therefore, we output true, indicating that it is possible to reorder the array into doubled pairs. Now, let's take another example with the input 3, 1, 3, 6. The first step is to compute the frequency count, which gives count equals counter, 3, 2, 1, 1, 6, 1. This indicates that the number 3 appears twice, while 1 and 6 each appear once. We then sort the keys of count by their absolute values, resulting in sorted underscore keys equals 1, 3, 6. Next, we begin iterating through these sorted keys. Starting with the key 1, we observe that count 1 equals 1, but count 2 equals 0. Since count 1 is greater than count 2, it is impossible to find a valid pair for 1. Therefore, we immediately conclude that pairing is not possible, and the output is false. In the third example, we consider the input 1, 2, 2, 4. The frequency count for this array is count equals counter 2, 2, 1, 1, 4, 1, showing that the number 2 appears twice, while 1 and 4 appear once each. After sorting the keys by their absolute values, we get sorted underscore keys equals 1, 2, 4. We now start processing the sorted keys. For the key 1, we see that count 1 equals 1 and count 2 equals 2. Since count 1 is less than or equal to count 2, we reduce count 2 by count 1. This operation updates the counts to count equals counter 2, 1, 1, 1, 4, 1. This ensures that 1 is correctly paired with 2. Next, we process the key 2. Here, count 2 equals 1 and count 4 equals 1. Since count 2 is less than or equal to count 4, we reduce count 4 by count 2. This updates the counts to count equals counter 2, 1, 1, 1 for a clock, successfully pairing 2 with 4. Finally, we move on to the key 4. Since count 4 equals 0, there's nothing further to process for this key. At the end, we perform the final check and confirm that all counts are 0, indicating that all numbers have been successfully paired. As a result, the output is true, meaning that it is possible to reorder the array into doubled pairs. To analyze the time complexity of our solution to the array of doubled pairs problem, we break it down into individual steps. First, we count the frequencies of all elements in the array using the counter from the collections module. This operation requires a single pass through the array, making it O(n), where n is the length of the array. Next, we sort the keys of the frequency dictionary based on their absolute values. Sorting involves a comparison-based algorithm, and if there are m unique elements in the array, this step takes m*log m time. However, since the number of unique elements cannot exceed the length of the array, m is always less than or equal to n. Therefore, the sorting step is bounded by n*log n. After sorting the keys, the algorithm iterates through them to check and adjust the frequencies. For each key, it checks whether the count of the current number exceeds the count of its double, and this check is performed in constant time, O(1). Additionally, it reduces the count of the double by the count of the current number, which is also an O(1) operation. These steps are repeated for all unique keys, resulting in O(m) time for this loop. Since m, the number of unique keys, is at most equal to n, this step is bounded by O(n). Combining all these steps, the overall time complexity includes counting frequencies, sorting keys, and iterating through them. The counting and iteration steps are O(n), while the sorting step is O(n*log n), which dominates. Therefore, the overall time complexity of the solution is O(n*log n). Now, let's analyze the space complexity of the solution. First, the frequency counter created by the counter object stores the count of each unique element in the array. If there are m unique elements, the space usage is proportional to O(m). Since the number of unique elements m is always less than or equal to the total number of elements n, this is bounded by O(n). Next, the sorted function generates a list of unique keys, which also requires O(m) space, and again, this is bounded by O(n). Finally, no additional data structures or recursion are used in the solution, so the auxiliary space is negligible at O(1). Combining these factors, the overall space complexity is O(n), which is determined by the counter dictionary and the sorted list of keys. Let's compare this optimized solution to a brute force approach. A naive method might involve iterating through the array and searching for each element's double or half for negatives. For each element, this search could take O(n) time, resulting in a worst-case time complexity of O(n squared). The optimized solution, however, uses a frequency counter in sorting, reducing the complexity to O(n*log n). This improvement is significant, especially for larger arrays. The space complexity of both approaches is O(n), though the optimized solution achieves its efficiency by minimizing redundant operations. Looking at best, average, and worst-case scenarios, the time complexity of the optimized solution is consistently O(n*log(n). Even if the array is already perfectly paired, the sorting step always dominates. Similarly, for arrays with no valid pairs, the algorithm still performs the same operations, making the runtime consistent across all cases. Finally, when we consider the mathematical proof, it becomes clear why the sorting step dominates the overall time complexity. Counting and iterating through the elements are linear operations, each taking O(n), which adds up to O(n), or simply O(n). Sorting the unique keys, however, involves O(m*log(m), where m is less than or equal to n. As n increases, the growth rate of O(n*log(n) outpaces O(n), making sorting the critical factor. In summary, the solution is highly efficient compared to the brute force approach, with a time complexity of O(n*log(n) and a space complexity of O(n). By leveraging sorting and frequency counting, it handles large inputs in a scalable and optimized manner. When working on problems like array of doubled pairs, there are some common mistakes to watch out for. First, incorrect indexing in the pairing condition is a frequent issue. For example, the condition ARR 2*i plus 1 equals 2*arr 2*i might be misapplied to indices that go out of bounds, leading to runtime errors or incorrect results. To avoid this, ensure that you're only applying the condition where 2*i plus 1 is within the valid range of the array. Another pitfall is neglecting edge cases, such as empty arrays or those with a single element. For example, an array like or1 might already satisfy or fail the condition without needing further checks, so these scenarios must be explicitly handled at the start of your solution to avoid unnecessary complications later on. Inefficient brute force methods are another trap to avoid. Generating all permutations of an array might seem like a valid approach, but since the time complexity is factorial O(n), this quickly becomes infeasible for larger inputs. Instead, lean on efficient methods like sorting the array or using a hash map to pair elements. Another issue is assuming the array is already sorted. If the array isn't explicitly sorted, solutions relying on this assumption, such as pairing smallest and largest values, will fail. Always sort the array as a pre-processing step when needed. Lastly, overlooking duplicates can break your pairing logic. For instance, if duplicates are not properly managed, you might fail to find valid pairings. A frequency map is a great tool here, as it allows you to track the count of each value and handle duplicates appropriately. To excel in interviews, there are a few key insights to keep in mind. First, recognize patterns in the problem. Pairing problems often boil down to sorting or frequency-based methods, so identify if sorting helps simplify the logic. Avoid brute force unless explicitly asked, as interviewers typically value efficient solutions that demonstrate your ability to analyze time and space trade-offs. Clearly communicating edge cases is another way to stand out. Discuss how you'd handle scenarios like empty arrays, duplicates, or unsorted inputs to show thoroughness. Testing your solution is essential. Run through examples to ensure your approach satisfies all constraints. Lastly, be prepared to explain trade-offs. For instance, why you chose sorting over a more complex method, or why a frequency map might be better than a two-pointer approach in certain cases. It's helpful to explore related problems to deepen your understanding. For instance, LeetCode 954, array of doubled pairs, directly involves pairing elements based on a doubling condition, making it the core problem here. LeetCode 923, threesome with multiplicity, focuses on counting pairs or triples with specific constraints, which is another variation of pairing logic. LeetCode 1005, maximize sum of array after k-negations, introduces sorting combined with strategic element manipulation, which is relevant for recognizing when sorting aids in problem solving. Lastly, LeetCode 846, hand of straights, involves grouping elements into consecutive sequences, which also requires careful attention to frequencies in pairing logic. These problems share overlapping techniques, making them great practice opportunities. There are several alternative approaches to solving pairing problems, each with its trade-offs. A common method is the sorting plus two-pointer approach. Here, you first sort the array and then use two pointers to iteratively pair elements that satisfy the condition. While the complexity is O, n log n, due to sorting, the implementation is straightforward and works well for sorted inputs. Another option is using a hash map for frequency counting, where you store the occurrence of each number and validate pairings through iteration. This method has a linear time complexity of O, n, for counting and pairing, but it requires extra space for the hash map, making it faster but more memory intensive. Finally, a greedy selection approach involves sorting the array and greedily pairing the smallest unpaired element with its double. This also has a complexity of O, n log n, and is effective for specific constraints, but it may fail when duplicates or other edge cases aren't properly handled. Understanding these trade-offs helps you choose the best approach for a given scenario. Great job on completing this problem. To wrap up, we reviewed the array of doubled pairs problem, discussed key approaches, and highlighted the importance of hash maps and sorting in solving pairing challenges. Thanks for tuning in, and we hope to see you for the next problem breakdown. Don't forget to like, subscribe, and keep practicing. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!